So we got a packed house. We're just taking the time to get everybody present and accounted for. Hmm. Okay. All right. So I got the brothers that were in that are here. If you're in the Zoom, you were on my roster. Let me see. Let me make sure my audio check. That looks good. Check. That looks good. Okay. Mic check. Mic check. Come on, guys. Who is this? I need your last name. First and last names, please be shown. Okay, that just makes things easier, so I don't have to do a crossword. I don't have to go searching. Let me see if there are any announcements. There are no major announcements other than usual operations. Okay, so this is the end of week 3, right? I think we agreed that week 4 we can anticipate exam 1, right? So we can anticipate exam 1 to open up a week from today at midnight. So like Tuesday night going into Wednesday, it should become available on Pearson. I've created it. I went on and loaded all of your quizzes and homework for the semester. So the only thing left are the exams, right? So the exams, I'm only going to make them available closer to exam time. So what that means is if you want to get ahead, like on, I hope you guys can hear me. If you want to get ahead on your assignments, you're more than welcome to. I want to say the lectures, as far as what I want to say, that's available as well because I made my sessions from the spring available. I'm just making a fresh set just for the sake of making a fresh set. Today, I would like to move forward into section 1.5. It's just, you guys are just basically live while I'm doing the recording. If you want to talk about a homework question or something of that nature, we can do that. And this is asynchronous, so you're not obligated to stay. Again, once you make it into my Zoom, you've gotten your attendance credit for the day. What I generally do with my college algebra students in the past, even when we were in person, I treated you guys like adults, right? You're in college now. Like this is the unofficial, like I forget the rite of passage, right? Unofficial rite of passage for American society, going from you know being under your parents to stepping out on your own and becoming an adult, right? So I intentionally treat you guys like adult. I put the choice in your hands. As long as you do the things that I ask, you know, I kind of don't stress too much about how you get it done. Just as long as you do what I ask, then I feel like that's a little bit more adult. So I try not to hound you too much, but I try to check on you, make sure you guys are okay, and you're at least connected with who you need to be connected with and having the conversations that you need to have. Um, so with that being said, so this is asynchronous. All the homework is available. The quizzes are available. The exam one will be available next Wednesday. I think I scheduled it. It should be ready to go. Um, I will give you this little nugget about the exam. I know I had some people disagree. Sometimes people leave and come back, but it's my recommendation. Like if I were a student experiencing this, even if I weren't paying attention, like if I was taking my class and if it was just too intense, I would just work on the homework during class. Like as long as you're doing something math related, you can even interject and get questions, ask questions during class because I'm just doing like the lectures to fill the space so that we're talking about math. If I'm not doing lectures, we're working on homework. There's a lot. I don't want to. I don't think I can. I don't think I can jam everything in there. Um, but I think I've said the main things that I need to say. There seems to be some chat activity. Let's see. Yeah. So what I'd like to do today is move on to section 1.5. As far as the exam next week, for next week exam, for exam 1, you're responsible for sections 1.1, 1.2, and 1.3, right? The official schedule that we originally like suggested was this week we're supposed to focus on 1.3. So, that's really where we are. I'm just doing live recording so that I'm just recording the lectures live so that we can kind of stay on track and keep up with the rhythm. So we're actually a little bit ahead. We got a little bit of wiggle room. Let me check the chat one more time. Nope, I didn't want to do a poll. I just want to check the chat. Let me see. No, as long as you're in here, once you make it into my Zoom, especially if it's before 15 minutes, you definitely get your attendance credit, right? I don't really be too strict about that. I only start really locking down if I notice people like I've had people come in like the last 5 minutes, and they generally like if they're just joining it at the 5 minute mark, 5 minutes left on the clock, I generally don't give attendance. I don't give credit for that. I might mark them as excused or something like that if they speak up, but let me give this student credit. But otherwise, we're gonna move forward. Now, my recommendation, if you're not interested in like section 1.5 yet, still stay on the call. Try to listen in, but just keep working on your assignments. Like if you don't do anything else, this is a great time to just go ahead and knock out your homework so that you can be ready for the exam. At least you want to have be comfortable with sections 1.1, 1.2, and 1.3, along with those corresponding quizzes. So this is a great time to just go ahead and do it. You get it knocked out now, you can enjoy your weekend. But if you shirk it off and don't do it now, you're gonna have to do it sooner or later. We all gotta suffer. Everybody suffers. It's just, do you want to go ahead and get past the suffering now so that you can reap the rewards, or do you want to put it off and not get the rewards and still have to suffer? We as humans, that just seems to be what it's going to be. We just have to suffer. Like it seems like we don't have a choice in that matter. So if we all are going to suffer, then you decide which end of the spectrum you want to be on. You suffer early and reap the rewards, or do you shirk it off and you suffer at the end but you don't get the rewards, right? Right? So yeah. Once you get into my Zoom, you've gotten your attendance credit, right? So that's the main thing. And again, my recommendation is just to listen in, work on your homework, knock it out, get it done so you can enjoy your weekend, right? But if you got to go, I totally get it. No biggie. That was the agreement. Okay. So yeah, I'm gonna take some time. We're gonna start making our way. This is gonna be an official recording for section 1.5. So let's look at it. So we're continuing chapter 1. Now this one can get a little bit intense. Let me go ahead. I'm going to suppress the audio. Feel free to use the chat or raise your hand if you have a question or need attention. Let me see. Yeah. Yeah, let me kind of keep going. I'm going to let that stay for right now. So section 1.5 are on transformations of functions. So some objectives here. We'd like to define transformations of graphs. We want to use vertical and horizontal shifts to graph functions. We want to use reflections to graph functions, use stretching or compressing to graph functions. So I'm glad I'm doing it this way. With my class earlier today, I went on and did a few more homework sessions. So, and all of these sessions I'm live streaming. So you definitely want to kind of check them out, and see what we talk about in each of my classes, because I'm kind of doing different things with each class and kind of making it so that you need my videos to get a complete picture, right? It's a little bit more work, but it's on file, so you don't have to like do it. You got a good amount of time to make your way through this stuff. But yeah, what we did earlier was we continued some more practice with section 1.2. But yeah, I intentionally saved this for this time because I know that this topic is it can be a little bit verbose, or it can kind of take a little while. So I intentionally saved it for the 2 o'clock hour so that, I'll have about like 3 hours to get through this. It doesn't take that long to get through all of this, but I wanted one clean take. Okay, let's keep going. So transformations, right? If a new function is formed by performing certain operations on a given function, then the graph of the new function is called a transformation of the graph of the original function, right? So like, I don't know if anybody plays Mobile Legends, but they just had this Transformers event, right? We all know Transformers. So trans is change or move, and form is shape. So like when you see the word transform or transformation is moving or changing the shape. So it's the same thing here. I ain't gonna lie, I did summon on again, this is just for my Mobile Legend players. I summoned on that banner. Somehow I actually got what's his name, Optimus Prime and Bumblebee. I was like, whoa, okay, that works. So just being a big kid, really, just being a big kid. I was totally irresponsible, but I was like, okay, well, let me just have my fun, and then I'll just make sure everything is in order. Which I encourage you to do the same. Have fun. No moment is guaranteed. We all here striving, and there seems to be this thing about gratifying putting your gratification off towards the end of your life, but you got to find a way to have fun along the way, and find a way to do what you got to do, but have fun while you're doing it, right? That's my recommendation. That's just for being happy. I don't know that that's necessarily a form for getting wealthy. you got to talk to somebody that's like has like a billionaire for that. But if you want to be happy, just find a way to do what you got to do, but have fun doing what you got to do. Something like that. Anyway, so let's look at this. So we have this function f of x equals the absolute value of x, g of x equals absolute value of x plus 2, and h of x is absolute value of x minus 3, right? We're asked to sketch the graph of these functions on the same coordinate plane and describe how the graphs of g and h relate to the graph of f. Make a table of values and graph the equations. I'm going back and forth. Let me get this student. I think he's in the ends. There he is. I'm kind of going back and forth with like, okay, do I want to like write all this out and do it manually, which will take more time, or just use what's already created? Let me think. Yeah, I think I'm just going to use what's already created because I feel like the concepts are not that difficult, right? So if the main function is absolute value of x, and we're going to create a table of values. So we're going to just choose some values of x. I think it's going to be like -3, -2, -1, 0, 1, 2, 3. We're just choosing values of x and then finding the corresponding f, the corresponding g, and the corresponding h, right? So if we glance at the table, so this is kind of everything already done, right? So again, the values of x over here on the far left, we just chose those. So -5, -3, -1, 0, 1, 3, 5, we just chose those. What's the absolute value of -5? Well, absolute value is the positive distance a number is away from 0, right? So the absolute value of -5 is 5. Absolute value of -3 is 3. So on and so on, right? So then this column for absolute value of x, I think is fairly straightforward. Now, with this first manipulation, this first transformation, what we're doing, we're taking our original function, which is absolute value of x, and we are adding 2 on the outside. We're adding 2 on the outside of our function, right? So notice I emphasize outside manipulation. So basically what we're doing, we're taking all these results and adding 2 to them. We're taking these results and adding 2, so on and so on, right? So 5 plus 2 gives us 7, 3 plus 2 gives us 5, so on and so on, right? So when we look at the graph, when we graph all of these ordered pairs, x and y, or x with the first column, the second column, and x with the third column, so you see over here to the right, the blue is the original function. That's just absolute value of x graph like normal. So notice when we added 2 on the outside of our basic function, that's like adding 2 to all the y values. What do you notice happened to the graph? Did we distort the shape? Did we change the position? Did we get a mirror image? Right? It should be clear that we move the graph up, right? So that's actually our first transformation, is that when we add a positive number outside of our basic function, it moves it up, right? So we're definitely about to get into like this. I'm about to show my age, so just bear with me. But we're definitely moving into like a Mortal Kombat combo, like up, down, left, right. These concepts are simple. It's just not easy, right? I think this one slide by itself is very simple, right? We're adding 2. We just graph these 2, absolute value of x versus absolute value of x plus 2. We graphed it on the same plane, and it's clear to see that the transformed graph, which is the red one, moved up by 2, right? But the reason it's simple, but it's not easy, is because this is just the first of at least 8 of them, right? So a lot of concepts in college algebra, they're very simple, but it's definitely information overload. So you have to like slow down, take your time, and you have to give yourself time. And what I mean by giving yourself time is starting as soon as possible. If you try to wait to the last minute to like do stuff, you're not giving yourself time. You're basically backing yourself into a corner. So this is why I'm trying to get ahead and like encouraging you to get ahead, because the best thing is just to give yourself as much time as possible to look at this stuff. And again, because we're doing remote, that kind of, I feel like it should alleviate or relieve some of the pressure as well, depending on how you work it. So let's look at this next one. So we're taking the same x values and the same base function with its absolute value of x, right? So now instead of adding 2 on the outside of the base function, now we're subtracting we're subtracting some positive number on the outside, right? So when we added a number on the outside, it moved it up, right? So now what do you think happens when we subtract a number on the outside, a positive number on the outside? What do you think is going to happen? All right? What does your intuition tell you is going to happen? All right, so let's look at this. So I think the first two columns are the same, but now if we subtract 3 from all the y values, 5 minus 3 is 2, 3 minus 3 is 0, 1 minus 3, so on and so on. We subtract 3, okay? And if we plot all of these ordered pairs, again, the blue graph is the original graph of absolute value of x, and then the red is when we subtract 3. So what do you notice happen? So now when we subtract a positive on the outside, I know it sounds weird because I'm saying subtract a positive, but that's what we're doing. When you subtract a positive on the outside of your basic function, it moved it down that many units, all right? So adding a positive on the outside moves it up. Subtracting a positive on the outside moves it down, okay? And notice that both of these manipulations are outside of our basic function, right? So if outside manipulations move it up and down, what's the next logical flow, all right? If outside manipulations move it up and down, what do you think happens when we move to the inside? So that's a primer. Hopefully, I'm sparking something in your mind, right? So to kind of summarize the vertical manipulations, so given some positive number, the graph of f of x plus that positive is going to be the original graph shifted c units upward, right? So again, if we add a positive on the outside of our original function, then the new function is going to be the original function shifted c units up. Similarly, if we subtract a positive on the outside of our original function, then the new function is going to be the original function shifted c units down. Okay, hopefully that's okay. So you add the positive on the outside, it moves up. You subtract the positive on the outside, it moves down. So again, outside manipulations seem to cause vertical shifts. So what do you think an inside manipulation might cause? Let's see the inside. Okay, so here's the next one. So given now the function that we're going to consider is x squared, all right? And now instead of subtracting 2 on the outside, we're going to subtract 2 on the inside and see what happens. We're going to add 3 on the inside and see what happens, all right? What does your intuition tell you, right? Hopefully you're thinking, so if we do an inside, if an outside manipulation causes a vertical change, then an inside manipulation, hopefully you're thinking, causes a horizontal change, right? So inside manipulation should cause horizontal. One other thing now, if we subtract a positive, should it go left? Would you anticipate it going left or would you anticipate it going right? Again, if we subtract a positive on the inside, should it go left or should it go right? If we add a positive on the inside, should it go left or should it go right? Let's see what happens, right? So we're going to make a table like we did before. Choose certain values of x, find the corresponding y for f's, find the corresponding outputs for g, and plot the two graphs side by side, okay? So we chose these x values, -4 to 4. So then we squared each of those. -4 squared is 16, 9, 4, 1, so on and so on, right? So then the first manipulation we want to consider is, let me see if this student, is he from my next class? Because I don't see him on my roster. He seemed like he popped in and out. Let me just make sure he's not in the waiting room. I think he might be in another class. His name looks familiar. Anyway, so now the first manipulation we want to consider, suppose we subtract a positive on the inside, right? We're anticipating it to move side to side. My question for you is, do you think it's going to move to the left or do you think it's going to move to the right, right? Okay. So now, when we subtract 2 on the inside, let's see what happens. So if we said -4 minus 2 would be -6. -6 squared is going to be a positive 36, right? -3 minus 2 is -5. -5 squared is 25. Let's keep going. -2 minus 2 is -4. Squared is 16. There's that 16. This one is going to be 9. And then now you can kind of see the pattern. You can keep filling in all those results. And then notice this one kind of shifted like that, right? They all are the same at that point on, right? And then similarly, for when we add 3 on the inside, I see the chat activity. I'll be there in just a moment. Now we're adding 3, right? So -4 plus 3 is -1 squared is 1. You see it there. -3 plus 3 is 0. Squared is 0. So on and so on. So you should be able to fill these in. And notice when we added 3 on the inside, they shifted in this fashion, right? So now let's plot those and see what happens. Yeah, let me kind of finish this and then I'll check the chat. So the blue is the original. So the green is where we subtracted a positive, right? You think it's left or you think it's right? It should be okay. I got it in my mind. All right. Let's real quick. Yeah. Okay. Let's just look at the graph. We subtracted a positive on the inside, and it moved. If we started here, the green went to the right when you subtract the positive on the inside. We started here, and it went to the left when we added a positive. So that might be counterintuitive to your intuition. It might be counter to your intuition, right? Because you subtract the positive, you would think it would move in the negative direction, but actually it was the reverse. It moved in the positive direction, right? Yeah. I'm trying to see if I can give you a good explanation. In order to produce the same y value, best way I can explain it right now is just the reverse tends to happen on the inside. So when you do inside manipulations, it tends to be the reverse of your intuition. In order to produce the same y, when we had x minus 2, it's like basically we added 2 to all the x's. So it's like you had to use x plus 2 in order to produce the same y. Um, again, the best way I can articulate that is basically the reverse of your intuition. But if you were to plot all those points, you would get these graphs and you'll see it. So you just kind of have to be aware that inside manipulations are generally the reverse of your intuition, right? That's about the best explanation I can give right now, without being overly complicated. Let me look at the chat. Yeah, yeah. If you're in once you get into my chat, if I don't say anything, that means I've given you attendance credit. Unless it's like 5 minutes left on the clock, or it's like really late in class. But you're fine. It's okay. I got you for attendance. Let's see. Let's keep going. Boom, 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 boom. Okay. So let's. So we've discussed 4 transformations. When we add a positive outside our basic function, it moves up. When we subtract a positive outside our basic function, it moves down. When we add a positive inside our basic function, it does the opposite of our intuition. It moves to the left in the negative x direction. When we subtract the positive on the inside, it moves to the right, right? It's kind of the reverse of our intuition. So all 3 functions are squaring function. G is obtained by replacing x with x minus 2 and f, right? So the x-intercept of f is 0, but the x-intercept of g is 2, all right? So for each point x comma y on the graph of f, there will be a corresponding point x plus 2 comma y on the graph of g. Yeah, it's just kind of circuitous is the word that I'm trying to use. Now I don't know if I'm using that properly, but it seems like it's talking in a circle almost. The simple explanation for me is just it's the reverse of your intuition. But this is what's going on for each x comma y on the graph of f. There's going to be a corresponding point x plus 2 comma y on the graph of g. So the graph of g is going to be the graph of f shifted 2 units to the right, right? So that's an okay explanation. If I think about it some more, I can probably clean up the articulation, but that's the gist of it. And then for h is obtained by replacing x with x plus 3 and f, right? So the x-intercept of f is 0, but the x-intercept of h is negative 3. And then it's a similar articulation like we just did for the other one, okay? Just the simplest way I can think to articulate this is the inside manipulations are generally are side to side and the reverse of your intuition, okay? So horizontal shift, okay, given some positive number, the graph of x minus that positive is going to be the original graph shifted c units to the right. If you subtract the positive on the inside, it goes to the right. If you add a positive inside your basic function, it's going to be c units to the left. All right. So again, it's a little bit wordy. The concept is simple in my opinion. It's just not easy because it is information overload. I do need to track down some students. I'm starting to notice that like there's certain people that I have not heard from. Like I think one guy may have tested out, but I'll track him down. That's no concern for you guys. Moving along. Let me see. Sketch the graph of this. I'm trying to decide if I want to do this one. Okay, I'll do this one. Let me see the time. All right, so let me get a copy. We're just doing the square root of x plus 2 minus 3. I'm just going to write it. So we got g of x equals the square root of x plus 2 minus 3. I just want to cut this. Let's cut, and I want to add a page. Okay, and we're going to work here. Let me do some other things. Paper, I like to write on graph paper. This is what we're working with. Cool. Okay. And let's do view, let's do seamless, and let's add one more page. Okay. All right, I'm gonna go ahead and close my attendance. I think most of the people that's gonna be here are here. Okay, so we're asked to sketch this graph. I'm gonna say sketch, right? So we're gonna use transformations, right? We're gonna make a table of points. Now, I'm gonna let my base function, I'm gonna let my f of x, the parent function is gonna be square root of x. Now, I don't know if you remember when we went through the library of functions, what I said this one looks like. Square root of x, I want you to think for a moment. For instance, what kind of numbers can we not take the square root of, right? For instance, what's the square root of 4? Square root of 4 is 2 because 2 squared is 4. What's the square root of 1? Square root of 1 is 1 because 1 times 1 is 1. What's the square root of 0? Square root of 0 is 0 for the same reasons. What's the square root of negative 1? Right? What number times itself gives you negative 1, right? So hopefully you should be able to see that square root is restricted to the non-negative numbers, right? You got to be greater than or equal to 0. The graph of square root essentially is the top half of a sideways parabola. Okay, so when we're choosing values of x, we need to choose non-negative numbers. Okay. So we're going to use transformations to go from f to g. Let me think about it. I'm trying to think of the simplest way. Okay, I'll make a table. Let's start off by making a table. So we're going to choose some values of x, find the corresponding f equal to this, and I'm going to do g. We'll do it in green. So g of x is going to be square root. I'm just going to do the whole thing. Square root of x plus 2 minus 3. I think the notes might do these in like a couple of steps. I'm going to try to do it in one. For my values of x, is this going to be too much of a challenge? I could do this. This might be a little more challenging because I'm thinking about that square root of x plus 2 giving us like decimals. So instead of doing that, I'm going to do it a little bit different. I'm still going to let that stay, but I'm just going to graph it, right? I don't want you to think about it this way. So let me think. Let me do an xy plane. So here's the x-axis. Positive x is in this direction. Positive y is here. Okay. Let's move this like this way some. We can move you like about here. That looks better. Let's go by ones. We don't need too many. We'll go like 1, 2, 3, 4, 5. Is that going to be too much? 6, 7, 8, 9, 10, 11, 12, 13. So I'm just doing somewhat of a rough sketch. Okay, I'm just going to use the transformations. I could probably cut a lot of this off. Probably should have focused on quadrant 1, but we're good. Here's the origin, and this is basically what I'm doing. Is like, let's do it like this: 2, 4, 6, 8, 10, 12. Right? So I'm going 2, 4, 6, 8. 2, 4, 6, 8, 10. These are negatives. 2, 4. Oh, that's not a 4. 4, 6, 8, 10, 12, 14. These are negatives. Okay. All right, let me see the time. Oh, we got right at about 10 minutes. Okay. And then one other thing I'm going to do, I'm going to change my paper to this. Okay, I think that's going to be easier for me. So first I'm going to graph f of x. So f of x is the square root of x. So for instance, the radicand, the part inside the radical, has to be greater than or equal to 0. So I can choose that x equals 0. When x is 0, y is 0. When x is 1, square root of 1 is 1. Next one I'm going to choose is when x is 4. So when x is 4, square root of 4 is 2. So we're going to have this here. And then the last one I'm going to choose is 9. When x is 9, y is 3. Right here. Right? And so the idea basically goes like this. Okay? So that's f of x equals the square root of x. Okay? So then now, I'm just going to apply the transformations. We'll see how the notes do it, to do a table, but I'm just going to apply the transformations, right? So if we do plus 2 inside the basic function, remember we said inside manipulations are horizontal changes, so it's going to go side to side. If we're doing a plus 2, my question is should it go to the right 2 by 2 or should it go to the left by 2, right? Remember, we said inside is the reverse of our intuition. So if we do a plus 2, it should, if we follow the origin, it should go left 2. And then that minus 3 is outside our basic function, so it should go down by 3, and we should finish here. Okay, so that plus 2 tells us to go left 2. That minus 3 tells us to go down by 3. And basically, it's going to be the exact same graph with those changes. So let me get a copy of this graph. Let me copy, paste, style. I want it to be this color green, right? So all we have to do, these are rigid transformations, right? So we said go left 2, so I'm just following that starting point. I went left 2 and down 3. 1, 2, 3, and that's the graph, right? So all it is going to be the exact same graph with those transformations. And again, I'm going to list them out. We went, this says to go left 2 units, and this one says to go down 3 units. So it's the exact same graph with those transformations. Okay. I'm going to go to view, single page. Okay. So that was the simplest way I could think to explain that one. Because I started to do the table. Let's see how the text, how the notes goes about that one. Delete that page. Okay. So let's see. Since C, let me go back. So we chose f of x to be the square root of x, and then g of x. Why did they do minus and negative 2? Oh, okay. Sketch the graph. Okay, so the general form is f of x minus c, so they had to get it in the proper form. So they said minus a negative 2, okay? And the d, they just kind of let it be, so that was a negative 3. So c was negative 2, d was negative 3. And then you see here, it says because c is negative 2, which is less than 0, the graph is shifted 2 units to the left. You see it here. And then because the d was negative 3, we went down by 3. So they essentially did the same thing that we did. We just did it in like one go. They broke it into 2. I thought that they might do a table, but they essentially did the same thing that we did. We just applied the transformations. Okay, let's try another one. Okay, that's okay. So So we've discussed 4 transformations. We talked about outside manipulations causing a vertical change. We talked about inside manipulations causing a horizontal change. So now let's look at some things that cause a reflection, namely a reflection in the x-axis. So the graph of negative f of x, again, notice this negative is outside our basic function. So there's something that holds. If we're doing an outside manipulation, it should cause a vertical change, right? So the graph of negative f of x is a reflection in the graph of f of x in the x-axis, right? So we take the original graph and we flip it over the x-axis. So notice that's a vertical flip. So if a point x comma y is on the graph of f, then the point x comma negative y is on the graph of negative f of x, right? It's like the y values go from positive to negative, right? So this is the first reflection. I think there are like 2 reflections. So to flip vertically is when you multiply the outside by a negative, right? Outside manipulation still causing a vertical change. So given some f of x in blue, if we multiply the outside by a negative, like we have in the red, it flips vertically over the x-axis. So that kind of continues. It's like the y's go from positive to negative. The x values stay the same, but the y values go from positive to negative. Let me see my time. All right, I don't want to keep you for. I want to keep you for right at about 6 more minutes. So if we multiply the outside, it flips it vertically. Then the next logical thought process would be, oh, well then does that mean that if we multiply the inside by a negative, does it flip horizontally? And you see it here. So if we multiply the inside of a function by a negative, then it flips it across the y-axis. So whenever we have x comma y, then the y values stay the same, but the x values flip sign. Okay. So combining transformations, explain how the graph of this can be obtained from the graph of absolute value of x, right? So whenever we're doing multiple transformations in one go, my recommendation, work your way from the inside to the outside. Just like in life, I mean, now this society that we're in right now, they tend to put more emphasis on the external stuff and they don't worry about the internal. And like a lot of people will be miserable. But I'm a pioneer. I'm not a pioneer, but I like to like focus on true happiness, not looking like I'm happy. So that's why I don't do like a lot of social media. I actually like take time to try to sort through my internal baggage. Right? It's a journey, but I feel like I'm positioned better for true happiness. Right? So I'm intentionally living my life to work my way from the inside to the out. But this is my recommendation for this as well, right? You want to work your way from the inside to the out. Not that the other route doesn't have its merit. It definitely has its merit. This is just what I'm choosing. So, and again, you'll start to notice that like a lot of stuff that we do here actually parallels life. It's the concepts that they actually carry over into your everyday life. Um, so if we're doing multiple transformations, we want to work our way from the inside to the out. So let's see. Explain how to graph. So the original graph is y equals the absolute value of x. So that's just going to be like a v where that v is at the origin, right? The first transformation, so then when we get to y equals absolute value of x minus 2, we subtracted 2 on the inside, right? So inside manipulation generally causes a horizontal change, and it's the reverse of our intuition. So it should take the original graph and move it 2 to the right. So this moves the original graph to the right by 2 units, right? The next change that we want to address, working our way from the inside to the out, is that negative, right? So now if we consider y equals negative absolute value of x minus 2, notice that negative is outside the original function. So outside manipulations generally cause a vertical change. Multiplying the outside by a negative should flip it vertically. So it's going to flip, we're going to say flip over the x-axis. Flip over x-axis. So that negative, let me highlight these. Let's see, I'll use orange. So this negative 2 caused it to go to the left by 2. Style. This negative here caused it to flip over the x-axis. Okay. And the next one, the final one I want to consider is that plus 3. So if we consider y equals negative absolute value of x minus 2, and then this plus 3, what this plus 3 is doing, notice that that's outside our basic function, and we're adding a positive outside, so it should move the original graph up. So it moves the original graph up by 3 units. And I'm going to write units. Units. Okay? So we start with the V. We should go to the right 2, flip it top to bottom, and then move it up by 3. All right? So let's see. So here's the original. It's just a V with the vertex at the origin. The first transformation moves it to the right by 2. Notice follow the vertex, right? It went to the right by 2 units. Okay, hopefully this is okay. So the next one we did was the negative, so it should flip it top to bottom. Wait a minute. Where's the rest of it? Oh, it's missing some slides. Is it here? Okay. Yeah. I don't know why they put that there. Yeah, anyway, that's kind of a summary of reflections. So if we multiply the outside by a negative, notice it from top to bottom. The vertex is still in the same position, but the y's went from positive to negative, right? And then the final one, we added a 3 on the outside, so it shifted it up 3 units. Okay, so right 2, flip top to bottom, and then up 3. That's why I said Mortal Kombat earlier, because it sounds like a Mortal Kombat combo finishing move to me. Left, right, up, down, A, B, A, B. Anyway, not that I've done that in forever. I don't even, we don't even have that kind of stuff anymore. But let me see. I'm looking at the time. Okay, so I'm going to put a pin in it right now. I'm going to go ahead. If you guys don't have any burning questions, I'm going to let you go. You're welcome to stay if you like. I'm going to continue with this because I'm live streaming, so I just wanted a full set. But the class is officially over for now, and I'm going to just kind of continue on with my next class, okay? All right, guys, enjoy your weekend. Just kind of get ready for exam 1 to open up next Wednesday. Make use of the Ask My Instructor, and definitely connect with the tutors and your classmates, okay? Enjoy your weekend. I'm going to keep working. So given this function, f of x equals absolute value of x, and g of x equals 2 times the absolute value of x, and h of x equals this, sketch the graph, right? So this is kind of a repeat. Let's see. Oh, so now we're looking at what happens when we multiply these functions. So I think we added and subtracted things inside and outside our functions. We multiplied negatives inside and outside. So now we want to multiply numbers inside and outside our function. So now we're going back to absolute value of x, and we're going to consider when we multiply the outside by a number larger than 1 and the outside by a number between 0 and 1, right? So we got our x. We just chose these x values. Absolute value of these, that's the second row. And then g is going to be, we take those results and multiply them all by 2. So times 2, times 2, times 2, times 2, times 2. And then h is going to be, we take those original results and cut them in half. So half of 2 is 1, half of 1 is a half, half of 0 is 0, half of 1 is a half, so on and so on, right? We multiply those to get a half. Okay, we're going to plot all of these on the same coordinate plane, and let's see what happens to the graphs. So the blue is the original function. Now, when we multiplied the outside by a number larger than 1, it got more like tall and skinny, or more narrow. When we multiplied the outside by a number between 0 and 1, it got shorter and wider. So that actually leads us to our next 2 transformations. When we multiply the outside of our basic function by a number larger than 1, then we call that a vertical stretch by that factor. When we multiply the outside by a number between 0 and 1, we call that a vertical shrink or compression by that factor. All right. So the red is like we took the y values and we doubled the y values but kept the x values the same. The green is like we cut the y values in half, but we kept the x values the same. And so this is the kind of effect that it elicits. So again, the graph of 2 times the absolute value of x is the original graph vertically stretched or expanded by multiplying each of the y coordinates by 2. The graph of y equals half of absolute value of x is the original graph vertically compressed or shrunken by multiplying each of the y coordinates by a half. Okay. So when you multiply the outside of your basic function by a number, let me see, here it is. So vertical stretch. If that number is larger than 1, it causes a vertical stretch. If that number is between 0 and 1, we call that a vertical compression. All right? If a is negative, first graph the absolute value of a by stretching or compressing, then reflect the resulting graph about the x-axis. Right? So if a is negative, first do it as if it was absolute value of a, and then multiply the outside by a negative, or just multiply it by a negative. Okay. Let's see the time. We got a few people hanging in there. Again, you're not obligated to stay because I know you might have other classes, but I'm still recording and streaming, so that's why I keep going, because you can always pick it up later and do what you need to do. And we're almost done. We got about 12 more slides. We've done 30. So we've discussed multiplying the outside by a number larger than 1 and an outside by a number between 0 and 1. So then the next logical thought is, oh, well, what happens when you multiply the inside by a number larger than 1? What happens when you multiply the inside by a number between 0 and 1? So let's see, the graph of original function f of b times x, so we multiply the inside, is obtained from the graph of the original by multiplying the x coordinate of each point on the graph by 1 over b and leaving the y coordinates unchanged. So the result is, let me see, so we get a horizontal stretch if the number is between 0 and 1, and a horizontal compression if the number is larger than 1, right? So intuitively, you might say, oh, if we multiply by the inside by a number between 0 and 1, you would think that it would squish it horizontally, but it's actually the reverse, right? So remember, inside manipulations are generally the reverse of our intuition, and they cause a horizontal change. So if we multiply the inside by a number between 0 and 1, it causes a horizontal stretch away from the y-axis. If we multiply the inside by a number larger than 1, it causes a horizontal shrink towards the y-axis. Again, these are both of these, again, because they're inside manipulations, are essentially the reverse of our intuition. Is everything okay? Oh yeah, move her. I am streaming though. Yeah. Okay. I am like sweating over here. I gotta go change the temperature. So it says, using the graph of a function in the figure whose equation is not given, sketch the graph of each of the following. Okay. So for this first one, we multiply the inside by a number between 0 and 1. Now, intuitively, you might say, okay, it's inside, so it should be a horizontal change. Oh, it's a small number, so it should shrink, but it's actually the reverse. So it should cause a horizontal stretch. So I want to say the y values stay the same, but the x values get doubled, right? So you should still have 0. This point here should be 2 comma 3. This should be 4 comma 0. Let's see for part A. 2 comma 3, 4 comma 0. So all the x values got doubled. So stretch the graph of the original by a factor of 2. So each x comma y transforms to 2x comma y, right? So it's just the reverse of your intuition. For part B, we multiply the inside by 2, right? Inside manipulation should cause a horizontal change. But again, you might be tempted to say, oh, horizontal stretch because it's a large number, but it's the reverse of your intuition. So it should be a horizontal shrink by a factor of 2. So it's like all the x's get cut in half. The y values stay the same, but the x values get cut in half. Okay? And you can see it here. So for every time we have an x comma y on the original graph, the new graph is going to have half of x comma y. Okay? Now we're multiplying the inside by -2. So first they said do the manipulation as if you did absolute value of -2. I think that's a student in my next class, so I'm gonna just kind of chill. I guess I could let him in. I'm gonna just kind of wait and try to get them all at once around right at 3 o'clock. So I'm gonna just kind of keep talking for 10 minutes. Hopefully I can finish this before they get here. So the absolute value of -2. So we should have the graph of part B, but if we're multiplying the inside by a negative, it should flip over the y-axis, right? So graph C should be the same as B, but flipped horizontally about the y-axis. Let's see. So this is part B, right? It was a horizontal shrink, and then notice it's the same graph but flipped over the y-axis. Okay, I'm going to try to wrap it up. Hopefully I can finish before my students get here. Sketch the graph of this function, right? So now we've kind of been primed a little bit, but because I'm intentionally using the graphs just for the sake of simplicity. So if we were asked to sketch the graph of something like this, we can use transformations, right? If you can identify the base function. So the base function or the parent function is, I'm going to just call it y equals x squared, right? That's the base function. Now, if we wanted to list out the transformations, again, we want to work our way from the inside to the out. So the innermost transformation is this -1. So if we subtract the 1 on the inside, it should move it horizontally. It's going to move it so that first transformation says to go to the right 1 unit. Okay? Now if we multiply the outside by a 2, so that's going to be a vertical stretch. Vertical stretch by 2. Right? We multiplied the outside of the basic function by a negative. So it should be a vertical change, so it should flip vertically. So flip over x-axis, flip over x-axis. I'm just listing out the transformations that we discussed. We added a 3 outside our basic function, so it should go up 3. These should be all the transformations listed out. This is the base function, that's the parent function, first transformation, second transformation, third transformation, final transformation. Okay? So we said, the first one we said was right by 1, and you see it already typed here. We got lucky with that one. The next one we said stretch vertically by a factor of 2, so it should get more tall and narrow. The x values stay the same, but the y values get double. So it should become tall and narrow. All right, you see it here. Stretch vertically by a factor of 2. Then we multiplied the outside by a negative, so we said flip vertically over the x-axis. And then shifted 3 units up, right? And this is the final graph. So that's using transformations. We're actually almost done. It didn't take me that much longer to finish this. I thought I was going to need more time. I think I can't really talk that much more, so I don't think I'm gonna do section 1.6 right now because I don't want to talk anymore. Let me see this one. We're gonna do our best with this one. So for an artery with radius r, the velocity via the blood flow at a distance r from the center of the artery is given by this formula, where little c is a constant that is determined for a particular artery. We write v equal to v of r, or v of r to be this function. Starting with the graph of y equals r squared, sketch the graph of v of r, given that the artery has a radius of 3 and a constant of 10 to the 4, right? Okay, let's plug this in. I don't think I need much more space. Let's plug in what we have. It says, starting with the graph of y equals r squared, sketch the graph of v of r. So let me make these substitutions. So then this v of r, let me use a different color so that it can stand out. This v of r should be, now it says that c is going to be 10 to the power 4, r is going to be 3, so 3 squared is going to be 9 minus r squared, okay? So now, if we start with what, y equals r squared, now we can do transformations. The first transformation that we did, we multiplied the outside of this by a negative, so that should flip over the x. So I'm going to say flip over x-axis. Okay? We added a 9 on the outside, so it should go up 9 units. And then stretch vertically by, what is that, 10,000? By 10,000, 10K. Okay? So we started basically with a parabola. We flip it top to bottom, move it up 9, and stretch it vertically by a factor of 10,000. So it should be tall and skinny with the y-intercept, with the vertex at 9. Let's see how do we do, right? So that's just describing the transformations. That's the main thing that I wanted to discuss there. I'm coming, guys. I'm probably gonna, let me see. Okay, they did all that, transform, stretch, okay, stretch vertically by a factor of 10,000, reflect over the x. Yeah, that's fine. I think that's essentially what we said. Okay. So the velocity of blood decreases from the center of the artery to the artery wall equals 3, where it ceases to flow. The portions of the graph corresponding to the negative values of r do not have any physical significance, right? So this is talking about blood flow as, what is the r as the, I think little r might be the radius. Little r is the distance away from the center. So the once you hit a certain distance away from the center, the blood flow stops. Okay. And the closer you are to the center, that's where the blood flow is maximum. That makes sense. The flow is the highest at the center, the closer to the center, and then the further away from the center of the artery you get, the lower the blood flow. And again, the negative values don't really have a weight in this context. It was really just focusing on that quadrant 1. Okay, that's pretty good. All right, cool. And I got like 2 minutes left on the clock for my next class. So with that, we're actually going to end the session here. I'm going to just kind of like reboot some things and kind of update some stuff. We're going to end the session here, and from one beautiful mind to another, enjoy the rest of your day. Peace.